Buongiorno. This will be the lesson for WebGL 101, and my name is Mr. Martin Naumann. I hope you have your sketchbooks ready to take notes. No, obviously not. I'm shitting you. Let's turn off the lights. Yes, this is better. So, hi everybody. Let me turn on the clicker. So I'm Martin. I'm from Zurich. I only know a very, very few words in Italian. One of them is a swear word that I'm not going to repeat on camera. And I'm really, really glad to be here. And I really love 3D stuff. I work with my team in Zurich in a company called Archeologic, and we do that. And it's quite cool, and I'd like to share this with you because I think on the internet you see a lot of sort of toys and demos and games that do 3D, but you don't see much more. That's kind of sad. And a lot of people that I talk to and like, it sounds really cool, but I don't know how to do it, and I didn't find good tutorials. So I'm gonna try to change exactly that. Also, if you can't hear me, can't read the slides, or if I'm too fast or too slow, let me know and I'll try to adapt. Because this is for you, not for me. I'm just like, whatever. So we're going to go through 3 topics, more or less. Actually, one is a lie. We're going to go through WebGL 101. I'm going to give a quick demo of what you can do and how easy it is to do stuff with ThreeJ, which is a framework for WebGL. And then we're going to go into WebVR, a bit of Augmented Reality as well, just tiny little bit. And then we're going to wrap it up, and you can then feel free to ask me questions the rest of the 2 days. Right. So first of all, WebGL is nice and fun and interesting to work with, not just because you can do random games and stuff, but for instance, this one is a story from New York Times. You would think a news website is kind of the boringest thing to work on, right? It doesn't have to be. And this is really interesting because they use progressive enhancement as well. So if you're on a computer or a phone where WebGL doesn't work or doesn't work well, you just see this in full width. And you get a normal news article with some pictures. And this one is about a couple of people climbing up a mountain. And I read that when I was on a mobile connection in Germany, and German mobile connections are horrible, so actually I dropped off every now and then, and I didn't get the JavaScript to make the 3D content work. So I just saw the news story, and I'm like, why is it such a big deal that they climbed this mountain? Because, you know, they actually, at some point, where is it? They actually brought booze. So they got drunk when they actually reached the top. I'm like, come on, if you actually can afford to get booze up, then how hard can it be? Then I revisited the story later, and I saw this freaking steep mountain. And as you might see from my belly, I love Swiss chocolate. And I'm not going to be able to actually climb that mountain. And I like how it enhanced my experience. I understood why this thing was tricky to do, and it was nice. And then there's also crazy stuff that you can do. So a map company called MapQuest went like, you know what's cool? Swiss mountains. You know what's also cool? Drones. You know what's really cool? Putting that into your browser and sort of combining all 3. So this is the Matterhorn, famous mountain. They climbed up on that, brought out a couple of drones with like laser scanners, and actually flew around the mountain, crashing a couple of drones in the process. You win some, you lose some. And then they had this, and this is metric fucktons points, so that's a large data set, but it works kind of smooth in your browser. And you can actually see how the mountain looks from all angles, and you can zoom in and you can zoom out, and it enhances as you come closer, which is really neat as well. There's also other scenarios like the company I work for. What we do is you give us a floor plan, an image of your apartment or office, and we make this 3D model that you saw earlier on. There's other companies that do CAD software. So you know Autodesk? Yeah, they now can do stuff in the browser as well. No more installing shit. Obviously not the really hardcore stuff, but actually you get a pretty good thing for 3D printing called Tinkercad, or now 123CAD. So this is really cool and nice. And there's a bunch of use cases. So I already said there's a use case for entertainment and games, obviously, right? Playing Doom in your browser. There's also a use case for medicine, actually. I've seen people, actually, I have a few doctors in my family, and they're like, it's a bit annoying that you have to like when they are not in the doctor's office, they have a hard time opening CRT images, like the brain scans and stuff, because you have to have specific software that requires a USB dongle. Try that with a MacBook Air, with the newest one that only has USB-C, and you forget your adapter, well, shit. But you know what? You always have a browser. So that would be really cool. And I mean, the web is all about that. It's about frictionless exchange of information. We have done this. We have solved this problem. Text, easy. Videos, kind of easy. Audio and images, also easy. 3D stuff hasn't been so easy so far. You either had some really weird shit, or a Flash or Silverlight or Java. Now you don't need that anymore. It works in the browser naturally. And you can actually exchange medical information without the friction of having to have specific software for that. You still need someone to actually sort of parse these things and display them in the browser, but hey, at least you now sort of can do this. Another thing is art and architecture and history. So just imagine you're living in Rome, which is kind of, or some of you might probably live in Rome, which is kind of convenient. I like Rome really much because I actually had Latin in school, and the only upside to that is actually there's two upsides. One is you can brag when you're in front of some really old European cathedral, and you can go, oh yeah, in the year 1765, this was built for, and then at some point you don't know a word, and then you just make shit up, and no one can prove you wrong, which is really cool. Or you actually sort of have the history part because we actually took a school trip, really long school trip to Rome and got to see all the nice places, Colosseum and Forum Romanum and all that jazz. But a lot of kids and teachers can't afford to do that. And now we can give them at least something better than just images and videos because they can sort of use virtual reality to sort of figure that one out. And that also works from the browser that we're going to see later. That's really cool. History, all the ancient stuff. There has been a hack that might be a hoax where someone scanned the head of Nefertiti because this thing is still in dispute. It's still in Berlin, but it belongs to Egypt. Tricky, tricky. Actually, it's not really tricky. Freaking politicians just get that thing back to Egypt. But politicians, be like politicians. Yeah, and then, as I said, image processing, CAD. So I've seen Felix Palmer, brilliant guy, giving a talk at a conference that I forgot about how to actually build sort of Photoshop in the browser. Nice. It's faster than Canvas because it has some cool stuff like shaders. So yeah, that's pretty cool. And there's just much more. For instance, maps and navigation as well. Seeing where you actually go is easier than just looking at it from the top view. Really nice stuff. Google Maps does that already in your browsers. Now the usual question comes, that's all nice and fine. How are we doing with the browsers? What's about Internet Explorer? Kinda good. Yeah, if you just ignore this and yeah. But comparatively good and actually kinda nice to have. So again, just still progressively enhance when you know that you can do, but actually for most cases, so for instance what we do, people come to us to see a 3D representation of a building. So we give you a pre-rendered image if you don't have WebGL, as simple as that. Oh, you have to have WebGL, nice, here, walk that, do stuff, change furniture. So there is scenarios to get around this, but actually the browser support is kinda good compared to other things. So now how do we do this? Well, at the very, very simplest level, we have a screen, which is a 2D space, right? This is a plane that I could point on and say, this is this far from the left and this far from the top, it's this point. Now we just pretend that it actually goes in and out of that, and we have a space. So this point here where my fingertip right now is, let me quickly readjust the microphone a tiny little bit. Perfect. And obviously on tape. So I hope now I don't cut out. So now we have this third axis where we can point where my fingertip is by saying it's this far from the left, it's this far from the top, and it's this far out or into the screen. So that's basically it. And the thing is, mathematicians are really, really picky about their words, so we have to learn a few new words. So this point on screen here, or there, which is no longer on the screen, but still a point, is a point. But mathematicians go like, don't use point when you're in 3D. I dare you, I double dare you. And we're like, okay, pinky promise, we're going to make up a new word. And we came up with vertex, or in the plural form, vertices, because English is fun. And so yeah, vertices are nothing else than just a bunch of points in 3D space. Vertices, nice. But I can have a lot of these points, and I still don't know how this sort of looks like. What if I have not 4 points, but 5,000? What shape do they form? Well, for that, we have a concept of the face. Faces can be triangles or rectangular or whatever, but it makes sense to use triangles because with triangles, if we just use enough triangles, we can sort of approximate every form. So you will never actually get a freaking circle from using enough triangles, but it freaking looks like it. All right? So triangles are like violence. If it doesn't work, just use more. Actually, don't use violence. Please don't. Anyway, beside the point. So here we have a large rectangle made up from 2 faces. And so these vertices are obviously just 3 numbers, right? How far from the left, how far from the top, or how far from the right and how far from the bottom, doesn't matter, but just be consistent. How far from the left, how far from the top, and how deep into or out of is a thing. That's 3 numbers. Okay, nice. Here it's 12 numbers, 3 numbers here, 3 numbers here, 3 numbers here, and 3 numbers here, 12 numbers. But what the fuck are these? Well, theoretically, they're also just lists of things, because we can say, okay, so if we number these vertices 1, 2, 3, and 4, we can say the first phase is just a list of 3 sort of numbers, right? Which is 1, 2, and 3, and the second phase is 1, 3, and 4. So it's literally just that. It's 2 lists. It's 2 JavaScript arrays. Hurrah, we know arrays. We're good. Cool. And then we sort of want to make it look nicer, because if you just imagine this to be green, then you have this kind of 90s feeling of how 3D works. But you want to make it look nice and gamey and cool and shiny, so we add textures. So a texture is nothing else than just an image sort of bent so that it fits the faces that we actually sort of map it onto. Here the mapping is rather easy because I have a texture which happens to be the same size as the shape that the 2 faces make, so I just put the pixels on and I'll be done. But WebGL gives you the power to sort of do that with spheres and with, I don't know, random shapes, with the shape of a head or whatever. So you really can be flexible about this. You can also use these images to cheat, but that's a very advanced topic. It's not so advanced, but it's too advanced for this short talk. So we map images onto this to make it look nice, which is texture. All right. Nearly the last vocabulary is 2 things. There's such a thing as which is called a normal vector, or a normal in short, and fragments. And if you imagine, so the first thing is, now we have pixels and we have math. So our vertices might, depending on, what the hell? The vertices, depending on how far or close they are to the screen, might be slightly different, and they are sort of, they might move very small and might be moving too small for the pixels we actually have, depending on what resolution we have. On a phone, it's probably okay. On a old 640 by 480 monitor, it might not be so okay. So we have to sort of break this down. So here we have the smooth lines that we actually have here. So this is a vertex, this is a vertex, and this is a vertex. And we have really nice smooth lines. But then the pixels screw us over, and they don't sort of go with the lines, so we have to sort of approximate that and do some calculations. The GPU does that for us and gives us basically just a bunch of pixels that we have to color in. Hurrah! And this is called a fragment. And the step that the GPU does is called rasterization. Now, we also might want to do some nice stuff with light. And to sort of explain how that works, if we look at this screen here and the projector is a source of light shooting a light ray or multiple light rays, luckily, because a single pixel image would not be so nice, shooting multiple light rays onto this surface. Now, if I have to calculate how much the light affects the surface, how do I do that? How the frick do I know? Well, I can sort of go through this intuitively and say, well, here's the light coming, here's my surface. I have a 90-degree angle between my surface and my light. But how do I express that? Well, you can also express it slightly differently and say, well, the surface faces in this direction, the light goes in this direction, and between the two is exactly 180 degrees. And this way, I have the full light onto my surface. If I now turn my surface by 90 degrees, it faces this way. Jesus Christ. I'm just going to stand here for the rest of the presentation. It faces this way, the light comes from this way, and I have a 90 degrees angle, and the light does not affect this surface at all. And then obviously all in between is some sort of, are 50 shades of gray or more. So here we see this effect. So this one probably faces exactly in the direction where the light comes from, while this is kind of facing away mostly. So how do we express that? Well, the thing is we can actually call this a normal, which describes the direction a face is facing towards. And we can calculate multiple. We can go, we can sort of take the face and then calculate the direction that each of the vertices faces. They don't really face, but sort of do, right? In collection with other faces around them. We can do this once per face, so every 3 vertices we have one vertex normal. We can all do these kinds of things, and then we get better or worse lighting. So this is what usually is referred to as shading as well, because we throw shades and we get shades of colors. Nice. Shading, however, can be confused with shader. A shader is a small program, basically a function really, a pretty complex function, but a function that runs on the GPU. And the cool thing is the GPUs can run like 1,000 of them in one go, because they have no dependencies. All they do is there's 2 kinds. One is they take a vertex and transform it somehow, move it somewhere else, for instance. This can come in handy when you have a camera and you sort of have to sort of move around points depending on where the camera shows, because you only have your screen and you want, like, if this point is here, this point will always stay here, but my camera might go this, but on the screen it then has to sort of also go away, and you can do that with a vertex shader. So it takes a vertex, which is these 3 numbers, x, y, z, the coordinates in space, and gives you new coordinates. That's it. No dependencies, no nothing. It's a pure function if you are one of the functional programming people. So it doesn't have any dependencies, so we can run it in parallel. Yes! Perfect. So we can run thousands of these in parallel. Nice. Then we have a fragment shader that gets the position in the fragment, colors, textures, lights, yada, 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 and actually just gives you the color that you're going to be putting on screen. This is not dependent on anything else, so it's also a pure function. Yes! We can run this in parallel too. Whoop, whoop, speed. And this is actually the really cool stuff that 2D canvas things can't do. They can't run in parallel because we have to use JavaScript to go over each pixel individually. And you're having a single thread that also does clicks and all the other things that you have to do. Oh no. But this thing actually runs in parallel, and hey, it runs off the main thread. Nice. So this is really quick. You can't write it in JavaScript though. You have to write it in a different language called GL slang, or GLSL for GL shader language. But it's not too complex. Highly recommend looking into that. Fun stuff. And the best thing is when these are buggy, it looks pretty. Win-win. And this is what we get from WebGL. This is called a pipeline. It's a bit small, so I'm going to read it out loud. The blue boxes are JavaScript. All the green stuff happens on our GPU. Oh, nice. And then there's this weird red box. That's the GLSL code that we can write and actually upload into the GPU. Nice. But it's not JavaScript, so it's not blue. I like blue. That's why I picked blue for JavaScript, because I also like JavaScript. Anyway, so here we have an array of vertices, and here we have an array of faces. Now we somehow need to get this into the memory onto the GPU. To do so, there's a concept called a buffer, which is just a bunch of memory on the graphics card. And we get this bunch of memory for our data and our data into this bunch of memory by saying, I want a buffer. So we get buffers for this. These buffers with the vertices then go into the vertex shader. That is our code that we uploaded or that someone else wrote for us and we use. That does the vertex transformations. It always has to be there. That's the thing. Even if it just takes the vertex and just outputs it again, it has to be there. All right. Then the graphics card, based on the vertices, the graphics card does the rasterization, telling us which pixels to color in and how much to color them in. And this information then goes into the fragment shader, which is, again, our code or someone else's code that we use that makes it colors on the screen. And these steps here happen in parallel. So we can paint thousands of pixels in one go. Awesome. And we can actually influence how these pixels are being which pixels and how these pixels are going to be colored in. So that's the pipeline. And that was all very theoretical and all very boring. Also very helpful, hopefully. But you know what? We're going to code now. And the thing is, the screen is a little small, so I'm keeping my hopes up that this is not going to look horrible. I already zoomed in a lot to make sure that you can hopefully read this. 11, shit, I should have done it in a different way. I should have done it like this. So this thing here, and it's online as you can see, already has code in, oopsies. Whatever, I leave it in and build from it. So it does a lot of setup in the background so that we don't have to do it, and this uses ThreeJS. And it's for you, online, you can play around with it and have fun. What it does is basically ThreeJS more or less works like making a movie. You have a stage. I love to say this on stage. You have a stage, you have objects, like I am an object, for instance, and then you have a camera filming me. That's the three things that you need to actually get something in 3D on screen with ThreeJS. You have a scene, you have some sort of object, and you have a camera. And then also you have one more thing, which is not really nice to explain, but it's a renderer. Because ThreeJS actually allows you to render using either the canvas, which is pretty slow but works, SVG renderer, which is super experimental and should probably not be used right now, and then the WebGL renderer, which just uses WebGL to get stuff on screen. ThreeJS has this concept of, so remembering the pipeline. In the pipeline we had faces and vertices. ThreeJS combines them and says this is a geometry. This is a convenience thing, and ThreeJS actually brings about a bunch of geometry so you don't have to do the math manually. So what we're doing here is we use a box geometry that has a certain size. It's a box, just that. But how does the freaking box look like? Because the geometry is just faces and vertices. We also need textures and colors and all that. That's called a material in ThreeJS, and here we have a mesh basic material. Mesh because we're working on a mesh and not on like random points. Basic, we're going to see what that means in a bit. And material because it's a freaking material. Then all we do is we put the mesh onto the scene, and then we render it and we rotate it around the axes. Rotation works with using radians, so I have to convert radians, and it runs with hopefully 60 frames per second, so I have to sort of break that down. And then I get, very unimpressively, this. Hurrah! That is all it took to get a very boring white cube. We can or actually spice that up a little bit by saying, you know what, I'll go all 90s and say, please only use the lines for the faces and give me a nice color like green. And then I get this. Also not very impressive, but hey, it looks kind of 90s, and I grew up in the 90s, so I kind of like it. And we can do other things as well. So I said that ThreeJS comes with a bunch of geometries. It has one geometry that I swear to God, the only reason I can imagine why it is there, at some day I will ask the guy that did the library why it is there, to do weird shit demos like this, because I don't see any practical value for it, but you'll see. The torus, not. And it's absolutely random, but I love it. So it's this weird thing. It looks like a pile of poo to me, but it's in 3D, and it's kind of a 90s pile of poo in 3D, so it's kind of cool. But still, you know, we might want to do something more interesting. We actually can do things in a more interesting way. What we can, for instance, do is, because this uses shaders, and shaders take everything as that basically is a color value as inputs for textures. Someone wrote this hilarious plugin, and I'm going to call it, I'm just going to call it texture, and it's a new webcam. I hope it's like this, texture. And then I can go in here and say, you know what, ThreeJS calls it a map because this is sort of like the 3D modeling term. It's a diffuse map, really, but it's the one map that you probably want. If you want one texture, it's a diffuse texture, which is just like, this is the color. And then I can say texture dot, this is a little weird, but okay, texture. And then on each frame, I say texture dot update. And if I'm lucky, my webcam turns on, and then there's this weird looking shape which is actually me trapped in this wee. Looks a bit like one of these racing car thingies for kids. If I revert that back to a box, it gets slightly more obvious what it actually shows. And now I can do the, I'm trapped, help me. And if it now actually would move this box up, you know what? We do this kind of science fiction kind of thing where the position Z, I can never remember. Honestly, I can never remember. We're just going to do like this. No, then it flies towards us. All right, I don't want that. I want it to fly out. So I'm like, help me. And I disappear in the distance. Not that it really makes that much sense, but hey, that was fun. I'll leave this up for a second. So we can also do random other things, like actually load objects. For this, I kind of need light, because virtual light, so that it actually works and looks nice. I can never remember the settings, but I'll try my best. So here we have one box that has a mesh basic material. And basic means it absolutely and entirely, actually I can leave this out because then it's going to just be white. No, actually now it's gone. Okay. Why? Oh, because I actually removed one. Okay. So this material, the basic material, ignores light entirely and goes, I don't care about light. And we can actually add other materials that actually take, for reasons of timing, take, for instance, the Lambert formula or the Phong shading formula, and then we get this. So here we have 3 cubes. One is super shiny. This is called Phong shading. One is sort of taking light into account, but doesn't shine. That's the Lambert material, and then there's the basic material. So here you can see there's a green light over here and a red light over here shining onto these cubes, and probably a white light shining from the front. So you can do these things. You can load 3D models. It's all fun and games. No. See, I'm always getting this one wrong. But let's not go into 3D stuff too much, like WebGL stuff too much. Have a play with this. Good. Now the more interesting things. The next step. So far we've been in front of stuff, which is fun, but it can get actually funnier. So this lady here thinks she's in a helicopter, and it's quite an exhilarating experience, and I tried a bunch of those. In Zurich, there is a few folks that built a bird fly simulator called Birdly, and you actually lie down on a contraption made from metal and all sorts of mechanical parts and wood, and you lie down on that, and you get an Oculus Rift and headphones, and there's a fan, a spinning fan in front of you, and you can actually, you have to do this, and then you fly. And it blows the wind in your direction, and you go, woo, and then the fan goes faster, and you go, woo, the fan goes slower. It's ridiculously exhilarating. And I entirely forgot that I was in a room full of people taking pictures of me and laughing and pointing fingers. So they're like, this is ridiculous. And I'm like, I don't care. It was fun, you know? And we can do this in the browser. Nice. So it doesn't have to be a Gear VR, though. Gear VR, I think, is $99. Oculus Rift, the prototype, was $599. The one that came out is like $799. It's pretty expensive. But there's Google Cardboard as well, which is like 10 euros or so. Where's mine? I got a travel-friendly one made from plastics, and it can adapt to the size of my phone because my phone is fucking huge. And it cost 10 euros. Free shipping from China because the European Union screwed up their trade agreements. So it's not that expensive. Yes, you have to have a smartphone, fair. But most of us at least have one, and I think this is only going to spread. There's a specification proposal. This is rapidly changing, but it's quite cool and quite nice to have. Both Firefox, like Mozilla and Google, work on it. I hope that others will jump on the ship as well. But you really only, sort of, for the basic experience, you need WebGL, and that's available in Edge and Safari and Safari on iOS as well, so you can get something. It gets better when you actually have full support, so let's see where that goes. Absolutely check that one out. Get a cardboard, really cheap. If you don't want the plastic version, just get a €3 version from China. Also really nice, or just go to conferences where they sometimes give them out. This one was from JSConf. They didn't tell me, and that was kind of weird because then it was about multiplayer WebVR, and then everyone in the audience had one. I'm like, oh God, I hope the server doesn't die. It didn't. Anyway, with Three.js, you're kind of good to go. All you have to do is you have to create a VR effect that wraps around your renderer. And this thing is the thing that actually splits your screen and makes sure that it actually corrects the cameras for both eyes. VR controls help you to actually get the movement from the sensors of the Oculus, for instance, or from a Google Tango sensor. If you have this tablet with a laser scanner that knows where in the room you are, we're going to see that in a second. It also uses the device orientation sensors or the Google Cardboard API on your phone, so that's also quite nice. And then you have that. That's it. On each frame, you update the VR control so that the camera moves with your head, and you render the scene using the camera, and that's it. And this is kind of, when you do normal Three.js, this looks more or less the same. And then you can do things like this. So a colleague of mine climbed the mountain and took this picture. You can do that with your phone. There's apps for taking photospheres. And then you can create, basically when you put that into a VR headset, then you can look around and it looks like you actually stand on top of the mountain, which is really cool. And it works by actually sort of mapping the world around on a plane and actually putting that around you, and it's rather simple to write. But that's like the lowest level of what you can do. You can also play around with something that Mozilla did, which is called A-Frame. It's a library in JavaScript that allows you to declaratively build WebVR experiences. So you load A-Frame.js in your head, and then you have your body of your HTML, and then you have a scene, and then you have a cube, and then you're done. And if you actually put that, you get a little button that says VR, you press on it, and then you put it into your headset, and you can actually look around, and there's a cube. There's obviously much more. You can control the camera, and so on and so forth. Definitely check it out. You're going to get the link in a second. But this is not all we can do. We're now also on the brink of doing augmented reality, because we have 3D stuff. We have camera access, thanks to WebRTC. Yeah, what else do we really need, right? We know position, we know that, so we can do stuff with it. So the simplest one was this one. I built this in like an afternoon because I was bored. This is in my guest room. It's just random objects and the camera picture, and I turn the phone and the objects stay in the same space. I also know the direction that you're facing in the real world. So for instance, the red one is north, which makes this room kind of nice. And that's a very simple experience. And this uses just the camera and WebGL. There's no magic in this. But we can get better at this, because this is kind of glitchy still. But this is called the Google Tango. And this is our office. And as you can see, I move around in the real world. And I also move around in the virtual world. If you look at the floor, the GIF is not perfect. But and now you might say, yeah, cool story, but this is a $1,000 developer kit from Google. Yes. But in June, there will be a $500 smartphone from Lenovo coming out, and $500 is not too much. Ask the iPhone people. It is expensive though, but still, it's going to become a commodity that our phones will probably have soonish, that you actually know where in the room you are. And that's the big selling point of more expensive VR hardware, is that you know where in the room you are, and you can track where the person is moving. And so far, the biggest problem with the cardboard was you didn't know when people actually moved around in a room. Now we kind of know. There's other problems with mobiles. I don't have to sort of go into the detail of that. VR with Oculus and stuff will still be better, but it's expensive right now. And cardboard is kind of inexpensive, obviously ignoring the fact that smartphones are not so cheap. And this is all that this demo really does. First of all, I use VR, the WebVR API. I ask for the VR devices. It's a promise API. Woo! The RX people will go boo. You get a bunch of devices. You take the first device, reset the sensor, so whatever way you face is 0. This makes sense, because if you have a menu in VR and you don't do this, then you put your menu at 0. I put it on like standing like this, and I see nothing. I'm like, what do I do? What do I do? This is shit. I don't see anything because the menu is behind me. With this one, even if I put it on standing like this, I get 0 and I get the menu and it's good. So it helps us actually orient the player as they come in. And then we start the render loop with this device. And the render loop is the request animation frame loop, where we do something for each frame. And we do this. We say, hey, please give me the state. And the state is two things. One is, where am I looking at? That's the orientation. My normal vector, kinda. And the position. Where in the room am I actually right now, right? Here's one position, there's another position, it's the same orientation. And then I set my camera accordingly. So this sets the rotation in this case. This sets the position. I'm done. This is all that the demo really does. No big magic. There's the promised links. Try this one. I highly recommend it. This one is cool because it uses what Boris calls, the author calls responsive VR. So if you don't have a headset, you get keyboard controls, mouse controls, and you can also tap a thingy and then use your phone at least. So it's kind of cool. Or you go into VR mode and then actually it splits the screen and stuff. There's the Google Cardboard guidelines. The quote from that was, put the menu in front of the user when he or she starts. That's one of the principles that Google Cardboard guidelines output. There's a bunch more. Avoid motion sickness and yada yada. Don't scare people too much because it's actually kind of scary when you actually sort of think that you are in the thing. Yeah. With that out of the way, my famous last words will be, Steve Jobs once said, the computer is the most remarkable tool that we ever built because it's kind of the bicycle of our minds. And to that I can only say yes, and VR is actually the second greatest tool because it's a freaking teleporter for our minds. So that's me, by the way. Take pictures of this one, not the other one. That's kind of boring. That's all over the internet. That's the real shit. Yeah, and with that, I'm through. Thank you very much. Slides are online. Reach me on Twitter, ping me, check out our product, or just chat with me. And I don't think we have time for questions left, but just find me. I'll be around. Thank you very much.